Okay, welcome to PLC 3 Week 9 State Manager. There's a little video here that you're watching it because you downloaded the PowerPoint and click that link right there. I'm doing the normal, no problem with attendance. That's all been good. I got new handouts. I didn't hand them out in the lab, but they're coming your way. Guide sheet. There's no homework here. There'll be no quiz, and then I'll have the lab here, and there really isn't that much D2L reading this time. There will be some pretty gnarly D2L reading next week. And so what it's going to look like is this. We have this kind of the state manager here, and that's what we're going to be talking about today, and then a state manager lab. I would think that this lab would go pretty quickly. Although I thought the PID lab, I wasn't sure where that was going to be. We're running a little bit over there. So hopefully we can kind of work these two together, and or the next lab, which would be the phase manager. And I can make that one a shorter lab if we're still overflowing and we need everybody to get the PID lab and then the state manager lab and then the phase manager lab done, because the goal would then, we would then move to servo and stepper motor controls. The servo motor control is going to need a state manager program in it. So that's the way that they operate. So we need to be sure we get the state manager and possibly the phase manager under control before we do that one. Or we're having so much fun here, we could take a look at sequential function chart, and I'll talk about it in this lecture here about how that ties in with a state manager. But maybe we'll just do regular servo control with some type of a state machine that you come up with. That's what we're building to here over the next couple of weeks. But let's take a second to review week 8, which was PID. And like I said, the lab, there's just about everybody still working on it, so we'll figure this out. It's a means to control a process utilizing a feedback loop. And then we went in there and we learned that we can kind of tune the loop. So some of the people are putting in different variables for the P and the I and the D, and then taking a look at the trend. We created a trend to see, do we get to our set point quickly, or do we take a long time to get to the set point, or do we get there too quickly? Do we overshoot? That's what we were trying to take a look at with the PID trend line. We just wanted to step back a little bit where we did the PID control is often using a simple PID controller. We did that 2 labs ago, but we moved to the PID instruction in RS Logic, and that's what's shown here. And so a couple things, it needs a tag name. I called mine PID1. And then my process variables here, I just made these tags with the appropriate data type. And then the main things to think about here are your set point. Here we set it to 400. And then, my process variable, that is what the thermocouple was reading in our case. And that, we ran a little, a fake simulation here initially to do the trend, and so that process variable would come up to the 400, and we would check to see how long it took and what the overshoot was and all this, and then we could tune it. Now, the goal for the last part was then to use a thermocouple to bring our process variable in and see if we could have it come up to that set point using pulse width modulation or possibly analog output. We'll talk about that again in a little bit, okay? And then I had some other tags here that I created here to utilize to pick off the data here from the PID. All right. So as I just said, the PID control can be utilized with digital or analog output. The last part of that lab was written with digital output, although analog would be a little bit more precise. I got a student, they promised to bring in some fans, or they're going to look for some fans, and they come in and we'll maybe do a little cooling process with an analog fan. Backing up to pulse width modulation, The PID digital control is achieved using pulse width modulation. And that's what we saw on those little PID controllers that we used, okay? And just to mess with it, we created a pulse width modulation add-on instruction that didn't have anything to do with the PID, but it was a way for us to, create our own little pulse width modulation, create a little trend line, and see, how that temperature came up to that. Most people liked that, thought it was pretty cool, and I thought it worked well, except for the relay output card that we cooked. Is interesting that, I equals P over V, and those were 200 watt light bulbs over 120 volts. So, we should have been, less than 2 amps, but that relay output card, one of them we burned out an output. So we're going to try and switch to 100 watt light bulbs. But that's a good little example of going back to 110 where you might just use your Ohm's law to calculate the amp draw, because that light bulb is just a pure resistive circuit. It's just generating heat, and we don't need to do any AC math on that. It's just straight away DC Ohm's law math. Anyways, when you created your pulse width modulation, you could have used a percentage of the range, and maybe that was a good way just to get an idea of it. You kind of locked in the temperature of it. I said dip it in cold water, and then whatever your set point is, kind of subtract the two and lock in the range, and then calculate your high, your medium, and your low, like 75%, 20%, and 5 for your heat pulse setting. When it, if it's greater than 75, leave that heat lamp on for a longer amount of time. As it gets within 25%, don't heat as much, and then when it gets within 5%, just blink that light just a little bit so that it heats slowly. And so that was a percentage. Now, the problem with that is when we go to the very last step and you want to use an actual thermocouple, we'll talk about this in a minute. You might have to modify your pulse width modulation add-on instruction a little bit. And so you probably want to save this just in case you want to use it differently somewhere else, all right? For example, you could have, probably on the last one, you probably need to recreate this and use like a set range. Like if it's, if you got something greater than 20 high heat, then when you get 15 to 5 medium heat and less than 5 low heat, maybe you want to use a range for that last part and create a new pulse width modulation. So we can program the PID instruction to control the pulse width add-on instruction. You want to probably save it. And the way that I think you could probably do this is if you recognize that the process variable, what you're reading on the thermocouple, will eventually equal the control variable. So if you look at my little chart here, you see the blue right there, I got set to 400. That's my set point, okay? And then so I got, this was actually cooling. I guess I just changed the variables to where it's coming down. And you notice it came down and it overshot. It came down pretty quick. Then it overshot, and then it came up, or excuse me, undershot, then overshot, and then, kind of converged on this. Well, I also plotted my control variable. And it's not my full error, but you realize that the control variable is in error. It's different than what my PV is, but these are going to eventually reach each other, and you notice that my control variable overshoots and undershoots, and then it eventually comes back in, and they're equal. So you could subtract your PV, your process variable, because that's going to try and hit 400. You said it, and it's reading, minus the control variable, which is going to be an error. And so initially, your PV minus your CV is going to be a very large number because you're off. And so that's where you go back to here. Maybe you set a range. Is if that the difference between the two is large, maybe you put on the high heating. But as the control variable starts coming under control, because your process is starting to come under control, the difference between the green line and the red line gets less and less and less. So then that maybe here on your pulse width modulation, you could have your different heating ranges, reflect that if you subtracted those. Now, The only thing is you got to watch PV minus CV getting negative, because a lot of times if this one is undershooting, this one's overshooting, and when this one's undershooting, this one's overshooting. So you're going to have to use your math and just be sure that, you know, you're maybe not using a negative number here, or you could get really creative with your math comparison instructions here, okay? And so that might be a way to utilize your PID and your pulse width modulation add-on instruction together to accomplish high, medium, and low heating range, all right? And the response is not going to be as nice as that trend that we did, that, you know, that simulation. It takes a while to heat up, and you looked at the trend, you understand how the numbers work, and you can probably put some numbers in there to get this to converge relatively quickly and smoothly without loading up the integral part of this, because when that integral loads up, this might mess us up a little bit. If we get too much integral on here, it might never let this control CV settle down like we want it to. So that's what we're looking for on the last one. You have to modify your pulse width modulation instruction a little bit, if that makes sense. Going back to the temperature that we did last time, you know, we did use different temperature measuring methods. Some people use the thermocouple card, some use the temperature transmitter and the analog card. We finally got a chance to look into some of those other temperature transmitters that weren't necessarily working, and they were thermistors. And so they're resistance based, which is not a problem because that's what the temperature transmitter does. They were matched for each other. They're made to make a 4 to 20. The moral of the story is we learned that wiring matters. We just had white, red, red instead of red, red, white, which affected the day work. But once we fixed that, those temperature transmitters were working. So hopefully we got enough equipment here to do this. We have only 4 heating stacks, and hopefully we're going to have 100-watt light bulbs in those. And so we just want to keep chugging and kind of share the equipment and be sure that everybody's got enough to make this happen. You know, maybe one, I don't know, just see where you're at with it, to see if we can keep everybody moving, if we don't have enough equipment. Week 9 is going to be short. Like I said, somehow we're going to, between week 9 in week 10, state managers and phase managers, we'll try and get pretty much all of this done and caught up before we move into the servo motor control. So a state machine, you've probably heard of this before. A state machine is a model that describes a finite number of states which can change in response to events or inputs. That's just kind of the Webster's definition of it, I guess. But what this is when we do with programming or processes, the way we utilize this is that we take turns being in one state at a time. So the state might be initialization, and the next state might be stamping. You know, however we organize our state manager, one state at a time. When we get into phase managers, it's just kind of a state manager, and the phase manager takes us the next step where basically you are running, and if you're not running, you're stopping, or you're aborting, or you're resetting, or you're starting again. So the phase manager is the higher version of this state manager, and basically it's just gonna once again process from one state to the next, but only in sequential order. But only one of the states can be active at a time. And we can accomplish this in RS Logics in a number of ways. We use the basic concept of the state manager in ELTE262 on our pneumatic stamp project. Now that was a long time ago when you were using the Slick 500, where we had the contactor, and something got stamped 3 times, and then you removed it, and then the conveyor came back on, and it got stamped 3 times, and all that kind of stuff. It's in the lab. You need to take a look at and review it. We're going to set that up again. But when we use that basic concept of the state manager, we use the done bit of the prior process, whether it was a counter, whether it was a timer, or cascading timers or whatever, to enable the rungs for the next process. So if we were timing 2 on, and then timer starts a timer, timing 2 off, when that timer got done, that made the next rung true, so that limit switches and everything like that would start the next sequence. Sequence 1, whichever that stamping had to be completed, for sequence 2 to work, and then for sequence 3 to work, and for sequence 4 to work, like that. So that's when we just introduced the concept of state or sequential control here. The system bit was probably the most basic concept of the state manager that we started visiting in that class, and that was that you had to have your system on, and you had a contact on your rungs and all your memory rungs and everything like that called system. So if for some reason you turned the system off, whether it was a loss of power or a reset button or an overload or something like that, the system bit goes down, and any rung that's got the system bit in it is opened, which would kill memories or reset counters or timers or whatever like that. So that was the most basic system when we understood that. What we're going to be doing is coming up initially with a sequence manager, okay? And it's often created by PLC programmers to control their processes. Each state is given a number. It might be, like 1 for initialization, because a lot of times when you're initializing or putting on a system, you're not going to be anything lower than that. And then you go in increments of 10, 20, 30, or 5, 10, 15, 20, whatever. Sometimes you space them out a little bit in case you need to add another process or another sequence between the two. And if you just went 1, 2, 3, 4, 5, and you needed to add 1 between the two, you'd be like, dang, I have to add 1 to everything. So a lot of times you'll increment them, okay? And when you do this, a lot of times the way that it's done is just have an equal instruction that checks for the value of the current state to enable the operation of the subsequent rungs. Whereas back here we make a done bit or something like that, or a system bit to enable the rung. Here you might use an equal instruction. And the state value during that operation, everything in state value of 10 might run, for example, and when it's done running, the last thing it does is advances to 20. And then everything in 20 will run, and when everything in 20 is done, it will advance it to 30 and at the completion of the state. So programmers will often develop their own state manager AOI. However you find that you like to use this, you can throw it into an AOI, and here's showing here an AOI and all the different orders, whether you're aborting or recovering, resetting, starting, cycling, resuming, stopping, whatever. And these are the out-of-state conditions here that you would be getting. And inside of this AOI, they've just got, if it's the current state is 1, then you're aborting. And there's a lot of code in here, but inside here is this code, and inside of this code as well is that if it's aborting, this is true, that there's a lot of things going on with aborting. And then when it gets done aborting, it would advance the out-of-state control to 2, and then it would be aborted. And then this would, any rungs that are related to aborted would occur, and then it would advance it to 3. And if it was equal to 3, it would, keep going, and it would recover and move on. So some organization of a sequence, and we're going to do one using in the lab to do that. I talked about sequential function chart manager. It's an ideal way to accomplish state management, because a sequential function chart looks like this, where you're at step 1, step 2, step 3 anyways, and then you have your process is stuck in here depending on what step you're on, okay? And the other thing that's cool about this is it uses, structured text in this. I did want to get into some structured text this time a little bit, and sequential function charts, just kind of a great way to do it. But it doesn't need to be. You could build a little state machine straight away with structured text if you wanted to, and it's basically if then, if your state is equal to 1, then light 1 on, and then run your stuff. Then if state is equal to 2, light 2 on, whatever. I I don't know where we're going to be at this. We'll see how you guys are doing with the state manager and get an idea of the phase manager. Okay. Um, the RS Logic phase manager, and that's going to be the next lab. And this has some capability that you might see in some type of a larger batch processing software. And Siemens makes stuff, and Allen Bradley makes stuff, and it's all built in so that when you click start, it moves, it schedules code so that you're going to be running, and if you click hold, it does the scheduling for you. You don't see it. It's all happening behind the scenes. That all of a sudden, things that are in these, I guess, subroutines or that have been scheduled get unscheduled or scheduled, but you don't necessarily see it like you do when you're looking at ladder logic. Okay. And then when we get into the phase manager, I got like 500 pages of great reading about how the state managers work here per national and international standards on process and batch control. Okay. Gonna be very exciting. Let's put it that way. So your SCADA systems, your supervisory control and data acquisition, is where all this comes in, and you're gonna see a lot of this out there, especially if you go and work at the Board of Water and Light or something like this. That's what you're doing. And in PID, in this case, it would look and act in a similar manner, but it might be just a little bit different in a SCADA type system. The individual processes control is local, and might be local and very specific. Basically, you're measuring the temperature of a vat or something like that. But it's probably part of a very big, larger system. If you got a gas turbine that's kicking out, electricity for the whole city, and there's a lot of systems going on, and you got a big SCADA system that's looking at it all. It's going to look a little bit different, and it's going to be a little bit more complicated. Okay, but it's basically the same. Another part of this is that an HMI often plays an important role in these PID and SCADA systems because that's where the operator has access to it. For example, we did the PID tuning. If you need to modify your process and tune it a little bit with your P and your I and your D, you can use the HMI to get in there and do it. Okay. Or if you need to get into your phase manager and see what's going on and stop it and restart it and abort it, you can tie the HMI into these state manager systems, and that's what we're going to be doing in this lab. Okay. So once again, most still need to finish that PID lab so you can get that last one work, PID with pulse width modulation, or you can try the analog. You might want to try the 12 VDC fan to create an analog cooling process. And what that would be is you just plug the light bulb in. Hopefully you don't blow up another relay contact, and then unplug it, because that way it's going to be hot, and then have this 0 to 10. 0 to 10 is what we could have. Try and have the fan control the cooling. And if you did it this way, basically you're going to take, like I said, the CV and the PV, the difference, and it's going to be like 1% or something, and you're just going to move that into your analog output. So your analog output is going to be scaled 0 to 10 on the output, and you're going to have a range. You're going to convert your temperature range to 0 to whatever 50. I don't know how much you're going to be cooling. You have to get a pretty good guess of how you're going to be cooling. And so, possibly if you're halfway to cooling, maybe you're only getting half the voltage out, which I guess would be 5 volts. Or you could put into a range if you wanted to, so that if you're still that difference is still a long way, then run that fan, at 10 volts. And then as it gets less, you could run it at 8 volts, 6 volts, 4 volts, or you could just make it linear. Like I said, once you reach a point, you could have that fan start to slow down the cooling in a linear fashion. All right. Otherwise, you'll use the PID to control the pulse width modulation. The state manager lab might be shorter. Let's get this done and see where we're at that, and then I'll take a hard look at the phase manager lab to see what we want to do. There's certainly a lot of fun stuff that we could do with that. Okay, it says no quiz because we didn't. We'll do the PID quiz next week. Whether you should all be done with the PID next week, and hopefully you're done or really far along on the state manager lab next week, and then we'll take the PID. And then there was no other homework because the homework on the state manager would be, I don't know, you'll have to look at the process just to see what I'm talking about and how it's doing. And then when you take a look at all the phase manager reading, those 500 pages that I talked about, maybe then I'll come up with a quiz, but it's not as theoretical. It's just grasping the concept and then programming it and seeing how cool it is and how it all works. So that was it, short and sweet, and have a good weekend.